lot of interesting stuff happens in the hallway. It happens, you get to walk out of a session and there's a collective experience that you just went through. And so there will be a hallway conversation that springs up discussing the material.
Can you RVO? How many people here have heard about return value optimization before? Please raise your hand. Okay, that's a lot of the room. Don't worry if you don't know it. You'll learn about it today. And how many people here would consider themselves to be experts at RVO? Please raise your hand. Okay, no one in the room, but that will change after this talk. So hi, my name is Michelle. I'm a software engineer at Bloomberg, where I write code for the order management platform that traders use to buy and sell securities on the exchange. Billions of orders flow through our system on a day-to-day basis, and every second counts. So performance is super important. I got my degree in computer science from Berkeley, where I was a teaching assistant. I am a member of the C++ Guild at Bloomberg, and I speak 5 languages. And for this particular audience, it's important to clarify that these are 5 non-programming languages. I speak many more programming ones. But honestly, it's possible that no one cares. And that's fine, as long as you care about return value optimization, aka RVO. So today we're going to cover what return value optimization is, the anti-patterns that prevent it from happening, and we'll also cover using RVO for performance gains. And I will take questions at the end. And we're going to have a little bit of fun today because I've actually brought stress balls with me from London, and they have these really cute messages on them. And I will be having questions during the talk. So if you answer correctly, I will give you a stress ball. And I'll work through the logistics a bit later, but pay attention because you get these really nice things. So return value optimization first made its way into the Zartek compiler in 1988. So for those of you that don't know, the Zartek compiler was the first ever C++ compiler to ship for Windows. And in 1989, it made its way into the C-front compiler. And in 1997, in the London meeting, it was added into the C++ standard. So if RVO has been around for a while, why are we talking about it now? Well, at Bloomberg, I have seen a number of cases where people have forgotten to use RVO in their PRs, and they have been reminded about it later, or even worse, they haven't been reminded about it at all. And sometimes people try to be smarter than their compilers, and they try using things like pointers, references, and a bunch of other things to try and get better performance improvements, when really it's just RVO that you need. And this is not a problem local to Bloomberg, because even outside, in the broader C++ world, this pattern repeats itself. People forget that RVO exists. And so what happens if I forget about RVO? It's fine, right? It's completely fine. Well, no, it's not, because you lose out on potential performance gains, and you also lose out on simpler, cleaner code. So what really is return value optimization? If you look into the C++ standard, and don't worry if you can't read the text, you'd be surprised to know that RVO actually isn't there. And this is absolutely fine, because RVO is a form of something known as copy elision, and that is defined in the standard. And in this section, there is a snippet that defines when copy elision is applied particularly when you have a return statement. And I could stand here and read that statement out. It might be too tiny for you to read, but it says, in a return statement in a function with a class return type, blah, 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 blah. That's what it says. At least that's what I read it as when I first tried to really understand what return value optimization was. And while this is a very useful specification, like Herb Sutter says, the standard isn't a tutorial. So instead, I went to my best friend, ChatGPT, and asked it what return value optimization was. And it told me that it is a compiler optimization that eliminates the creation of temporary objects by directly constructing the return value in the memory location of the caller. And what does that really mean? Well, if I have a piece of code like this, where on line 2, I create my object A, so I'm initializing it using my object 3, and then on line 3, I return it. And on line 8, what I'm doing is I have this local variable E1 that is being initialized from the return value of example 1. With return value optimization, what happens is instead of constructing my object 3 in the space allocated for local variable A on line 2, we construct it directly in the space allocated for local variable E1. So just to see a different perspective of what return value optimization is, this is actually the assembly of the piece of code you just saw. But on your left, the case where return value optimization is off, and on your right, where we have the case where return value optimization is turned on, there are differences. You don't need to understand assembly to understand this, because really, the most important thing here is that on line 4, we have the RSP, which is the stack pointer, moving down by 32 bytes in the case where return value optimization is turned off. But in the case where it is turned on, we move the stack pointer down by only 16 bytes. So we are using less space on our stack frame when we have the optimization. The other interesting thing here is that in the case where we have RVO off, we have this whole extra function call happening, which we don't even have in the RVO on case. And maybe I don't need to say this, but the number of assembly instructions in the case where RVO is off is way more than in the case when it is on. And yet another visualization, but this is your stack frame when return value optimization is turned off. What we do is we would construct my object 3 in the space allocated for the local variable A. But when we have the optimization on, we would construct it in the space allocated for local variable E1. And if we were to see these two diagrams side by side, we'd notice that indeed we are using less space on that stack frame for example 1. So return value optimization comes in two forms. There is the named return value optimization, which is NRVO, and the unnamed one. We have an example, example 1, and in this example, we're showing NRVO, because what we're doing here is we initialize my object A, and then we return this named variable. Since we're returning an L value, which is a named variable in this case, we call this named return value optimization. And example 2 shows us unnamed return value optimization. And what we really are doing here is we are returning an unnamed variable. We're returning a PR value directly. And you might be wondering, why do I need to know this? This is just terminology. Well, the difference is actually really important, because it kind of defines how your compiler, or whether your compiler, provides the support. So compilers are actually allowed to perform unnamed return value optimization since C++98. But they have to perform this optimization since C++17. And this is only for the unnamed version. of return value optimization. So in a way, unnamed return value optimization is guaranteed for you. There is no way to turn it off from C++17 onwards. But the named return value optimization, on the other hand, the support for that is optional, but it is recommended. We can do something a little evil. We can actually turn off named return value optimization. And we can't do this for unnamed return value optimization, again, in C++17 onwards, because remember, that is guaranteed. And also, you might be wondering, hey, if this whole NRVO and URVO thing sometimes is optional, does this mean that my compiler even supports it? Well, don't worry. All major compilers like MSVC, GCC, and Clang do support the optimizations. But again, we can turn the optimization off in GCC and Clang using this no-allied constructors flag. And we can do something very similar in MSVC, but we can't actually use this flag because MSVC disables NRVO by default, but it can be enabled using the ZC NRVO option, the O2 optimization, or the permissive options. So let's play around with a tiny example. So I have a class, my object, and it has a constructor, which prints calling OG constructor. And for those of you that don't know what OG means, it just means original, according to my sister. Yes, that generation. And we also have a copy constructor over here, which prints out the line calling copy constructor. We are running these examples with x86, 64, GCC, 13.2 as a compiler, and we are using C++17 with that no-allied constructors flag, which turns off named return value optimization. And C++23 produces the same results for all the examples you will see today. And of course, just to mention, this slide over here doesn't have the copy assignment operator and the destructor shown, but just assume that it is present. OK, so we have these examples. And example 0 just returns my object 3. And if we were to print out what happens, we just have the call to the vanilla constructor, because remember, the flag no-allied constructors can't actually disable unnamed return value optimization. But if we were to print out example 1's result, we would have an extra calling copy constructor line printed out. And the number of copies printed out actually depends on the version of C++. So you might have more number of copies in C++11, for example. But the important question here is, what are those copies? So the first possible copy that you can have is when you copy my object 3 from wherever it was constructed to the space allocated for local variable A. Your second potential copy is when you copy initialize the return value from A. That is, you copy the value from the local variable A into the return value slot. And your final potential copy is when you copy the value from the return value slot into the space allocated for local variable E1. And if we remove the no-allied constructors flag, we would have both unnamed and named return value optimization. And so there is no call to your copy constructor. But we have forgotten something. And ladies and gentlemen, this is your chance to win a stress ball. So do you know what we've forgotten? Anyone? You can yell it out. What was that? Anti-patterns. We'll come to that. We will get to that. That's true. But there's something here that we've forgotten. So we had our copy constructor and the rule of 3. Oh, that's a raised hand? Assignment operator. We do have that. So remember, we had rule of 3, and we mentioned it would be there. That's a good guess. Move constructor? Congratulations, you have won yourself a stress ball. Again, I'm a software engineer. I can't throw things, but here you go. Oh, I can throw. OK, never mind. Sorry, I tried my best. But that stress ball is for you. Cool. So yeah, we have forgotten our move constructor, because in C++11 onwards, there's something known as move semantics. And move semantics essentially just help you avoid that copy, and using an R-value reference, it is usually seen to be more performant than calling the copy constructor. So we can add the move constructor into that example we had and assume the rule of 5 applies. But in all the examples we saw, the same thing happens, except instead of calling the copy constructor, we call the move constructor. And so the question here now is, does RVO even really matter if we have a move? And I have an example over here where I have a for loop that runs 100,000 times, and in this for loop, I am just initializing A. And A is just the return value of example 1. And in this example, I am just constructing A and then returning it. Classic potential NRVO. So I have compiled my code with C++17. And in one case, I have the no allied constructors flag. And in the other case, I do not have this flag. So what I did was I actually just used the terminal function time to time this code. So very simple, very basic. And the question was, do we have a performance improvement? I won't give you a stress fault for this because it's probably too easy to answer. But the answer is yes, we actually did see a performance improvement, and it was very consistent. And if I were to use this nifty little speedup function to calculate the speedup, I would get around 26%. But this number isn't important, because the number that you get, the percentage, is just going to depend on what you do in your actual use case. It can vary significantly. The important thing here is the big green yes. Return value optimization matters. So when does return value optimization not work? So one, when we are evil and we disable it, like we did earlier. The other case is when the object construction happens outside the scope of the current function. So what we're doing in this example is we are initializing my object A in the global scope, and in example 1, we are returning it. Because we constructed A outside of the scope of example 1, there is no return value optimization being applied, because your compiler doesn't know that when I'm constructing my object 3, it needs to be returned in example 1 at that point. The other case where return value optimization is not applied is when the return type is not the same as what's being returned. So over here, I have this class called myObjectChild, which inherits from the class myObject. And I have another function called inheritance_fails_RVO, which returns the type myObject, even though it's really returning myObjectChild. And myObjectChild can use the same amount of bytes that myObject does. It does not matter. Return value optimization still won't be applied. The types need to match. We have yet another case where return value optimization won't apply, and that's when there are multiple return statements returning different objects. And this applies to only NRVO. So we have an if branch over here, and in one case we return x1, and in the other case we return x2. At compile time, your compiler does not know which branch it is going to hit because of that random function over there, literally RAND, random. And because of that, there is no optimization applied. The other case where we don't have this optimization is when you're returning a complex expression. So if it is something that is not a vanilla L value or PR value, then you don't have return value optimization. As rule of thumb. Yeah, that's all I'm going to say for now. So this applies to only NRVO. And the other case is for not guaranteed RVO, either a move or copy constructor is sufficient. So if we go into our example and we delete the copy constructor as well as the move constructor, and in example 1, if we initialize A and then return it, this code isn't going to compile. But if we were to return a PR value instead, this code compiles perfectly, and you have unnamed return value optimization. Isn't that great? OK, we're going to have time now for stress balls. We have questions, and what you need to do is answer whether return value optimization is applied in the example I will show you. And the logistics for this is that when I show you the example, you have a choice. You can raise your hand if you think that there is return value optimization in the example, and you can keep it lowered if you think there isn't. And I will throw a stress ball at you, potentially. And this is a random algorithm depending on my throwing skills. And is someone keeping their hand raised for everything? Sorry, what was that? That is true. You can go brute force and keep your hand raised for everything. I might pick on you to answer things and explain your answers, potentially. But yeah, that's how it's going to work. I will throw a stress ball at you, but if you've answered incorrectly, you have to give the stress ball to someone who has answered correctly. Yep. Don't be sad. It's good. It's fair. OK, so the setup for each of these examples is going to be as follows. We have my object E0 that's being initialized from each of the examples you're going to see. And we have the move and copy constructors we had previously with the rule of 5. Everything is perfect. First example, we have my object A, and we change one of the member variables of A, and then finally, we return it. Do we have return value optimization? You can raise your hand if you think there is return value optimization, and keep it lowered if you think there isn't. OK. The answer is, actually, I'm going to throw it at someone. I'm going to throw it at, I think, who answered first. And I hope I have really good aim. Oh my God, I'm impressed. You are right. So there is return value optimization. Congrats on your newly earned stress ball. And just to explain what's happening here, when we have that no-allied constructors flag, we have that extra calling move constructor printed out, because we're turning off named return value optimization. And when we don't have that flag, the optimization is applied, which is why there's only calling OG constructor, the vanilla constructor that's printed out. Next example, we have auto instead of my object. Do we have return value optimization? Raise your hand if you think there is, and keep it lowered if you think there isn't. OK, most people have raised their hands, and I'm going to throw it to who I think answered first. I have really, really good aim. This is really good. Yeah, return value optimization is applied in this case. Auto doesn't change anything. OK, are we ready for the next example? Woo! Yeah, so the next example is returning std move A. Do we have return value optimization? Raise your hand if you think there is, and keep it lowered if you think there isn't. OK, we have 1/4 of the room, maybe a little under, that's raising their hands. So the fun part here, no, you can't lower your hand now. Keep it. The fun part here is that we don't have return value optimization. And I'm going to throw this well, I can't actually tell who answered first, because, OK, this is going to be a random throw. Yeah, so there is no return value optimization, because we have a std move A. This is the complex expression that's not a vanilla L value or PR value. And this is something I've seen a lot in Codebases. So please do not try to std move things if they don't need to be std move. Because again, without that std move, we would have only the vanilla constructor being called. But now we have the move constructor as well.
I think Clang always tells you not to.
Yeah, Clang does. We'll actually get to the tooling part. That's a very good point. Do you want a stress ball? Is that why you answered? OK. Next example. What we have here is we are constructing my object x1 and my object x2, and then we have an if branch. And in one case, we return x1 and the other x2. Do we have return value optimization? Please raise your hand if you think there is. OK, we have a few hands raised. So unfortunately, the compiler does not know that it's going to return x1 or x2 at compile time because of the random function, right? So we don't have return value optimization. OK, I'm going to throw this stress ball randomly. Oh! Nicely. No people were harmed during this presentation. I will throw nicely. Yes, yes, I'll come. It's very soft. Question? So the question was, the compiler basically, you don't understand why the compiler doesn't know which object is being returned. Yeah. Yeah, exactly. It's the exact same amount of bytes in either of the branches, right? So it's a good question. Why doesn't a compiler know? And that is a good question for people who write these compilers. I actually have the same question. And I think maybe the compilers need to be improved, potentially, to know. In the case where the return type is literally using the same amount of bytes, just make the optimization. But there are things you can do to just improve your own code so that you have the optimization. And we'll cover that. Great question. No stress ball yet, because remember, questions at the end get stress balls. Question? Yes? Good question. We'll get to that at the end, because it requires a bit of explanation. But yeah, good questions. OK, next question for stress ball. We have a very similar example, except we have const myObject. Do we have return value optimization? So the return type is const myObject, but we are returning myObject. So raise your hand if you think there is return value optimization, and keep it lowered if not. OK, a good amount of the room is raising their hands. So I didn't see who raised their hand first, so this is going to be a little random. I won't hit anyone. Did you answer correctly? Yes. Good, good, good. All right, so yeah, there is return value optimization in this case. So CV qualifiers don't actually affect whether you have return value optimization or not. So it doesn't matter if you have const over there, because you still have the optimization. That was simple enough. What about this case, where we are returning a ternary? So we return, if a is greater than 50, we return x1, else we return x2. Please raise your hand if you think there is return value optimization. OK, we have one hand. Imagine if you were right, you get the stress ball. But nice try. There is no return value optimization here. And what's terrible about this is we have 3 calls to OG constructor, not 2. We have x1, x2, and then the third one's present because we're returning that ternary. And we also are calling the copy constructor, even though we've defined the move constructor, right? So just to prove my point, I moved the ternary outside of the return, and now we just have those 2 OG constructor calls. So what you can do to improve this code is you can actually std move it. And if you std move it, you don't have that extra OG constructor call, and you don't have that extra copy constructor call. But what is even better, in my personal opinion, is doing something like this. So what we're doing here is we're using unnamed return value optimization. So it is still a ternary, but what we're doing is we're replacing x1 and x2 from the previous example with myObject3 and myObject5. And we don't need the std move here, because we have unnamed return value optimization. And we have just one call to the OG constructor. And I know some people here are glaring at me because they probably hate ternaries. So you could also do something like this. Just write out your if branch and then return myObject3, else return myObject8. So this also uses unnamed return value optimization. And people might be saying, oh, this is terrible. I don't know what's happening here. It's better to use a variable name. And I've actually gotten this comment on one of my PRs, saying you should not use magic variables. I'm sorry if my colleagues are watching this. But yeah, I see that perspective. But I think if you comment your code and just name your class as well, it's better to do something like this than what we saw previously. Next example. Do we have return value optimization here? So we are constructing myObject x1, And then we have an if branch, where we return x1 in both cases. Please raise your hand if you think there is return value optimization. OK, most of the room has their hands raised. Again, this is going to be a random function throwing stress ball. Nicely, nicely, nicely. Whoops. Nice catch. OK. There is return value optimization here, right? Because the compiler knows what it's returning. What about here, when we move x1 inside of the if branch? Do we have return value optimization? So we have two calls to x1. Please raise your hand if, so two calls to my object 3. Please raise your hand if you think there is return value optimization. OK. There is no return value optimization here. People are sad. I'm sorry. But the reason for this is because your compiler doesn't know which branch it's going into, and so it just doesn't get the optimization. Compilers are not completely smart. Yeah, true. But it is what it is. What if I did this? So it's very similar to the previous example. So I'm going to go back a bit just to show you what changed. But in this example, what we have is we have x1 in the first case and x2 in the other case. But what we've really changed is our compiler. So in the previous example, we had GCC, but now we have Clang. Do we have return value optimization now? Please raise your hand if you think there is return value optimization. Yes, there is return value optimization. And I will throw the stress ball. And I think people who... Great throw by me. Yeah, so we have return value optimization here. So GCC could have potentially become smarter and done something like this, but it just isn't smart enough. That's fine. We can work around it. And in all the other examples you'll see today, Clang and GCC behave the exact same way. This is just one of the exceptions that we will see. So in general, they work the same way, but this is a good exception to just know about. OK, this is slightly out of scope because it is a throw and not a return. So obviously, return value optimization does not apply because it's not a return, it's a throw. But do we have an extra call to the move constructor or copy constructor when we throw something instead of returning it? So please raise your hand if you think there is a call to the move constructor, and keep it lowered if you think there isn't. OK. So there isn't a call. Sorry, there is a call to the move constructor. So people who raised their hands, it means you said there was a call to the move constructor. So I'm going to give it to the person. Yes, yes. Now you can catch. I can throw. OK, I can't throw. But you caught it. But yeah, there is a whole extra move constructor call when you throw things. What about now? When instead of just throwing it, I try to throw it, and then I catch what I've thrown with a reference, and then I return that value. When I return E, is there return value optimization? No. OK, y'all are right. There is no return value optimization. And I don't know who said no. Oh, OK. Then in that case, it's going to be a random stress ball. I'll give it to someone in the front, maybe. OK, never mind. I'm glad that cup had a lid on it. Cool. So the reason I'm showing you this example is because in production, I have seen cases where people have code where they try something, and then they catch it in a particular function. And then in the next, so they rethrow in that catch, and then in the next function, which has called that function, the previous function, it does the same thing again and again. So throwing doesn't really help with performance if you throw multiple times. So just be mindful of this example. And just FYI, removing this reference near my object and %e will still mean that there is no RVO. Next example. So what we're doing here is we have a parameter for the function, and we then pass in my object 3 as the parameter, and then we finally return that variable. So we're returning A. Do we have return value optimization? Okay, raise your hand if you think there is return value optimization. Keep it lowered if not. Okay, we have 1/4 of the room raising their hands. So there is no return value optimization here. I love how when I say there isn't, people just drop their hands. That's good. But it's OK to be wrong. It's fine. But yeah, we don't have return value optimization here because my object 3 is in a way constructed outside of the scope of example 7, although you can argue it's kind of in scope. But just be mindful of this example where we don't have return value optimization. And yes, I will throw a stress ball. Please look in case it hits you. But good catch. Question?
Is it possible to compare just optimize the whole function?
The copy constructor and the move constructor, you mean? The whole function, what do you mean? This example, right? OK, so the question was, is it possible the compiler optimizes the whole function away, as in it wouldn't call the function, or? No, it will still call example 7. It wouldn't optimize it away, at least for GCC. And sorry, what was that? Oh. OK. I will. OK. Yeah. So the answer was, because we have the O0 optimization, then we won't have that optimizing the whole function away, basically. Yeah. Thank you for answering that. And actually, I will give you a stress ball somehow. Cool. Great. He's already Bloomberg. OK. Next example. So we have, I think, 4 more examples. All right. So this example, we have class myObject2. And we just have a vanilla constructor, move constructor, and copy constructor. We have another class, myObject. And this class has a member variable b of type myObject2. And it has the same move, copy, and vanilla constructors as we saw previously. Do we have return value optimization? Wow, just hand raised. OK, yeah. Do we have return value optimization if what we're doing is we return x1.b, where the type of x1 is the type myObject, but x1.b is of type myObject2? Please raise your hand if you think there is return value optimization. OK, we have 1 hand, 2 hands. So there is no return value optimization in this case because at the time of x1's initialization, the compiler just doesn't construct that member variable in the return value slot. It just thinks about x1 only. So I will throw the stress ball again randomly. Yep. What could we do to improve this code? So what we could do is actually have a function that constructs b and then returns it. And this does have a catch. Of course, if you are calling getB multiple times, that's not good, because that means you're calling your OG constructor or your vanilla constructor multiple times. But if you are only going to call this once and then pass your return value around, maybe something like this actually is better. And so if we did do x1.getB, we would have return value optimization in this case. So you've optimized your code. What about this, where we return a plus equals 1? Do we have return value optimization? Okay, we have 1 hand raised, 2 hands raised, few hands raised. So we do not have the optimization, because remember, this is not a vanilla L value or PR value. It's a complex expression. I'm going to throw this randomly. Let's do someone in the corner, because I don't think you guys have gotten any, but it's very funny watching people catching. Question?
What would happen if you put the a plus equals 1 on its own line and then return a?
That is fine. So the question was, what if we had a plus equals 1 on a different line, not in the return, and then we return a? So that is the same as example 1, actually, when we're changing the object a, and we're returning just an L value a. So that means we have named return value optimization. Good question. Okay. Example 10, so we have three more examples. What we have here is volatile. So I think Ben Dean did a talk about this earlier today, which I may or may not have missed. But volatile essentially tells the compiler that the value of the variable may change at any time without any action being taken by the code the compiler finds nearby. So it's basically saying, hey, compiler, please don't optimize my code. And if we had volatile in front of the parameters in the move and copy constructor, and if we had an example like this, where we have my object volatile A, do we have return value optimization? Please raise your hand if you think there is, and keep it lowered if not. Okay, we have a few hands raised. So there is no return value optimization here. And that's because we're telling the compiler, don't optimize it, right? We're telling it. So I will throw a random stress ball. Let's do this corner, not hitting the projector. Yeah, I'll try. Whoop. Thank you. Oh, the same person got it? No, good. Cool. What if we remove the volatile? So remember, we still have the volatile in the parameter. So we have my object volatile, reference my object. So the move and copy constructors still have it. But we have removed it from our example. Please raise your hand if you think there is return value optimization. OK, so even though our underlying code did have volatile, because we don't have volatile here, we're actually fine. The optimization is still applied. So this kind of, I think you were first from my perspective. So, and I will also give one to the person at the back, because you guys were very similar time-wise. Oh! No one got hurt during this talk at all. OK. We have return value optimization here, and this is nice because even if you have underlying libraries that you call into that use volatile, and depending on how they use it, actually, you might still be able to get return value optimization if you do the right thing. Example 11, so this is covering structured bindings. So we have a wonderful little std pair. Oh, quick question. So the question was, in the volatile case, what happens to unnamed return value optimization? We'll get to that actually at the end. So I'll keep all questions at the end. Really good question. OK, and also remind me about it in case I forget. OK, over here in example 11, we have a std pair that's made up of my object 3 and then another my object 3. And we return it, and the return value is then assigned to A and B, so using a structured binding. And finally, we return A. So there is return value optimization in the first part of this, when return to my object pair returns its value. But the question is there return value optimization when we return A in example 11? Please raise your hand if you think there is return value optimization, and keep it lowered if you think there isn't. OK, we have a few hands raised. There is no return value optimization here. So structured bindings just means no RVO. How about Clang? Actually, we can try this at the end and see what happens. But I believe Clang does the same thing. But we can, yeah. OK, I will throw this at someone. Well, I tried. So what we could do here to make this piece of code better is we could make two separate functions, return A and B respectively, and then we just get our normal return value optimization. OK, this is the last example. Hopefully, I'm doing OK with time. But this is a very fun example. And I'm going to actually throw 3 whole stress balls for this, because this one tripped me up when I saw it the first time. So what we have here is we have my object A that's being initialized or constructed. And then we return A, but A is in parentheses. So this means it's no longer a vanilla L value or PR value. Do we have return value optimization? Please raise your hand if you think there is return value optimization, and keep it lowered if you think there isn't. Okay, we have barely 1/4, not even 1/10 of the hands raised. So there is return value optimization here. I'm going to throw 3 stress balls at the first 3 people I saw. And okay, you're really tricky to throw this to. Yes, I won't do that. Yep. Cool. So this is, okay, I will throw one more. Oh my God, this is really tricky. That was the camera. Thank you. All right, so those are all the examples, but quick warning from what we just saw. If you are writing a copy or move constructor, never make the constructor do anything else other than a copy or move. And why is that for a stress ball? Yeah, optimize the weight. Were you going to say the same thing as well? Okay, 2 stress balls it is. 1 for you, and 1 for you. So yeah, the constructors can get elided, so don't put anything important in there. So we're going back to the standard, and don't worry if you can't read this. I'm going to zoom in. What we have here is just the conditions for when return value optimization is applied. So it does say, when the expression is the name of a non-volatile object, so we have seen this example before, with automatic storage duration, and just, we've not really seen this explicitly, but if you have something that doesn't have thread local, static, or extern, and there's essentially memory allocated at the beginning of that parentheses, so the closing block, and deallocated at the end, that just means it has automatic storage duration. So it's a little trivial, but good to know. Other than a function parameter. So we did see the case where we have a function parameter, and this means we didn't have return value optimization. Or a variable introduced by the exception declaration of a handler. So we did see an example of this when we had a variable introduced by the exception declaration. When the return type is the same. So we do need the types to match, and we saw this example as well. Ignoring CV qualification. Remember the const example? We saw that. When those conditions happen, the standard says we have return value optimization. So we have understood the C++ standard. Well, a part of it, but same thing. So now it's time to go into your code base and change everything so that return value optimization is supported. Please raise your hand if you think we should be doing this. Yeah, a lot of hands raised. Really appreciate it. This is absolutely a great idea. This is fine. Okay, so this is not actually a good idea. It's actually a micro-optimization. Because if you have maybe a flame graph that looks something like this, where you have function 1 and function 2, and function 1 calls 2 functions, function 1a and function 1b, so they're asynchronous functions. If you try to optimize for return value optimization in function 1a, and even if that gets shorter, function 1b is still going to, run for however long it's running. And so function 2 will still run at the same time. So you're not optimizing your actual workflow. So what you could do instead is use return value optimization when you see a bottleneck. And of course, you'll only know where a bottleneck is if you use profilers. So I do have a few written up there, but there are honestly a lot of profilers in the C++ ecosystem. So pick your favorite one, go with it, find your bottleneck. The bottleneck may not be return value optimization. It might be IO bound. It might be anything. But if it is return value optimization, please optimize it. And of course, you can use return value optimization when you code and PR review. So you might be wondering, on a day-to-day basis, how do I really know that I am using return value optimization correctly? Tooling is very important. I think someone in the audience mentioned Clang Tidy earlier. But there are a number of tools to help you with return value optimization and knowing when to use it or how to use it. So Clang and GCC have a pessimizing move. So this tells you basically when you're using std move in an incorrect way. There's also warning C26479 in Visual Studio Code that tells you when you're using std move incorrectly. But my favorite one is WNRVO. So this is actually a relatively newer one, and it's in GCC version 14 and above. So it warns you if the compiler essentially does not elide the copy from a local variable to return value of a function. So essentially it tells you when return value optimization could happen, but it isn't happening. And from all of the other warnings, this one is my personal favorite. But it doesn't actually catch some of the anti-patterns we saw today. So you still do need to be a little mindful of what you're doing and keep everything you saw today in mind. So yeah, we have seen what return value optimization is. We've seen the types of RVO, the anti-patterns preventing it from happening, and how to use return value optimization for performance. So that's it. Thank you for listening, and I hope you enjoyed the talk. I will take questions now as promised. And I'm going to do something a bit fun. Maybe I don't know everything, and if you're able to answer the question, actually, let's do this. Let someone ask a question, and if someone else can answer the question, I will give you a stress ball. And if not, we'll figure it out together. How does that sound? Yeah? OK, any questions? Okay, question there?
Yeah, so when in GCC gets attacked with copy are there ways for RVO? Are there tools recommend to maybe format your code in different ways to apply those?
Yeah, good question. So the question was, essentially, is there tooling for Clang and GCC to format your code so that return value optimization is applied, right? Yeah. So the tools I found basically were these ones that I found the most useful. I think we can get better, though, with the tooling we have so that it can automatically format things for us. I do not know of any examples that do other than these, really. Does anyone know? If so, I can throw a stress ball at you. Okay, no one knows as well, because probably there isn't anything out there yet. So maybe this is inspiration for you to go and write your own tool, and then make it open source, share it with the rest of us. It's a good idea. Any other questions? OK, wait, many. OK, question here.
So wondering about the const expression and const eval. Like, will that lead to RVO?
Yeah, const expr and const eval. So I actually wanted to have an example here, but then I couldn't use it with my object because you need your const expr destructor. But let's actually try this at the end together and find the answer for that. And does anyone know, actually, off the top of their head? And I will give both of you stress balls, by the way, for questions. So one for you. So the question was, with const expr and const eval, do we have return value optimization? Does anyone know? Does anyone know? Yeah. So the answer was because the compiler can compute it and knows it at compile time, there's the optimization. Okay, I'm going to throw this nicely. Okay, any other questions? Okay, questions there? Right, so the question was, is a copy really that expensive, right? Because yeah, so the question is, is a copy really expensive? And yeah, you're right. So if you have a primitive type, like integers, doubles, maybe it's not that expensive, but then things add up. At least that's what I've seen in production. So when you have bigger objects, or even things called multiple times, those values do actually give you a performance hit.
So what's the percentage of performance you see in production by optimizing now? Is it 1%, 10%, 50%?
That depends. So the question was, what's the performance speed up that you've seen in production? So it depends on what you've optimized. So you can actually get very lucky where you see things that people messed up. Because, of course, when you're coding out things, maybe your focus isn't RVO. Maybe it is, I need to get this feature delivered. And so if people haven't done things correctly, and depending on how often that is done, you can change things, but the actual speed up is going to vary a lot based on what you change. So I don't want to give you an exact figure because it is really going to vary. But yeah.
Remember that a lot of objects don't just initialize, they also allocate. And that's a lot more expensive than the copies of the data themselves.
But for that, we have moves around. But also, yeah.
A lot of times there's a string in there somewhere or a vector or something, and that's a lot more expensive than just the data.
Yeah, so basically, Brett mentioned that sometimes allocating memory is what really gives you the issues, and that's really expensive. So it's something.
Is there an STL object it cannot do an NRVO?
Is there an STL?
STL object, the compiler cannot do NRVO.
Yeah, so when you have things where your move and copy constructors are not there, deleted, I believe coroutines sometimes have issues with this, but yeah, there are, well, there's on the library yet, so yeah, that's true.
Any objects are there that can't do NRVO?
I do not think so, as to my knowledge, but does anyone disagree? I actually believe 100% there isn't, but in case anyone disputes me. But yeah, okay, so no. And I will also throw stress balls at people who, Brett is good. Brett has too many stress balls. Okay, and then one for you as well. Cool. Okay, other questions? Question here? Yeah, so the question was, are there any cases where the optimization level is set to a certain amount but not the other, that return value optimization wouldn't be applied, right? So it depends on the compiler. For example, with O0 in GCC, you would still have return value optimization applied. You need to have that no-allied constructor flag. So it depends on your compiler in a way. Like MSVC is different, like we saw earlier, right, on that slide. But hopefully that answers it. Yeah. I will throw a stress ball at you nicely. Cool, near head miss, but yeah. Was there another question? Comment? Yeah. Yeah, so there was a comment. In addition to what I said, it also depends on the standard. That is true, depending on what the standard says, right? Is that? Yeah, that is true. So yeah, there is a distinction between C++17 onwards and before because of the whole things we saw earlier. But yeah, that's a good point. Let me throw this at you. Cool. All right, more questions? I see one there.
I have an answer to the question I asked earlier.
Yes, go for it.
So in context where depends on the compiler. Client has a bug and it doesn't treat it as a part of the discard.
Oh, that's very interesting.
Yeah, so GCC discard, GCC was correct for the GCC as well. Client access
Gotcha. So basically, it was, what was it? It was clang tidy? Sorry, no, what was the, clang tidy has the issue. So yeah, with context where clang tidy had an issue. Sorry, the clang compiler, my brain is mesh. But yeah, the clang compiler has an issue with context for, but the other compilers deal with it just fine. And stress ball for you. No? Yes. No? Are you sure? Okay, no. Yes. Okay, other questions? Question, yes.
For your example with the structured bindings,
Yeah.
perfect forwarding resolve that issue outside of ref?
So the question was, with the structured binding example, was it forwarding?
Perfect forwarding also ref.
Wait, I didn't hear that, sorry.
Perfect forwarding.
Oh, does perfect forwarding essentially solve it? I believe it may. I'm actually not sure. Does anyone know? Yep. Perfect forwarding is a move constructor. Oh, it's very interesting. I didn't actually think of that. Good question. Right. Okay, so it casts it to an R value, so it'll actually move it Yeah, will be. Now you want a ball. Okay, I'll give two of you stress balls.
Bindings are actually just the object itself. It doesn't actually be constructed into two separate objects. Just syntax reference. Yeah, it's just references to the inner object.
The structured bindings is just a reference to the inner object. Yeah.
So it's more similar to that. Like, to me, it's more similar to the example of returning a wrapper object that contains the other object.
Right, that's true. And yes, I will give you a stress ball nicely and not hit the projector. Close enough. Cool. And I shall give you a stress ball as well for your comment. Okay, you have too many. Cool. Okay, any other questions? I have 29 session is over. Okay, fine. If you have any other questions, feel free to come up. I also have a few more stress balls if you want a stress ball. Feel free to just, yeah. But yeah, thank you again.